So, one of my favorite sections, graphing polar equations. We're going to go over all the different types of polar equations that you'll be expected to know how to graph in your classes. The first ones I want to do are what we call the rose petal graphs. That's anytime you have something in the format of r equals sine n theta or r equals cosine n theta. And we'll talk about what n represents and how you can kind of figure out how to graph it based on just what n is. But first, let's just look at a couple of graphs with a pretty extensive table. Now, instead of the xy plane, we're graphing in theta and r. In terms of theta and r, theta is the angle that we make with the positive x-axis being 0 degrees and moving counterclockwise. R is our distance from the pole or the origin. So you can see, here's a table for this equation here, r equals sine 3 theta. You can verify these different values yourself. What I want to show you here is how we can take these values and actually sketch a graph with it. So this one, when theta is 0, we start with r being 0. That essentially tells us at this angle, we are right here at the pole. Now, when we move to an angle of pi over 6, we get an r value of 1. Now, what can be helpful before you start graphing is figuring this out before your graph. When is r at its maximum value? So, in this case, that's going to be when 3 theta, which notice 3 theta is what we're taking the sine of. We want to figure out when is 3 theta equivalent to the angles where sine gets its biggest value, its largest value, which is going to be 1 or negative 1. And that's going to occur at 90 degrees, or pi over 2, 270 degrees, or 3 pi over 2, 5 pi over 2, and so on. Then when we multiply all these by 1/3, we get pi over 6, pi over 2, 5 pi over 6, and that would keep going technically, but we're just going to need these values to start with. So we know at pi over 6, we have a maximum value of 1, and I've sketched a circle here to represent a radius of 1. So we know at pi over 6, we are going to be right on the edge of this circle because that's a radius of 1. Now, it works its way back. Remember, that's the maximum value we are going to get for this function. So at pi over 4, it's at this value. So somewhere, here's pi over 4, maybe somewhere around here, right? And then once we get to pi over 3, we're back to a value of 0. So that tells us that this is going to look something like this. It's going to come out, hit that point, come back in, right, like this. Boom. I'm not an artist, so these will look a little ugly at times, but we're going to do our best here. Now, as we keep progressing to an angle of pi over 2, we get an r value of negative 1. That tells us at pi over 2, we're down here, r is negative 1. Now, we could graph angles in between these, but we can tell from this shape that it's going to continue through like this and do about the same thing that it did there. Pi over 2, 2 pi over 3. We come back to 0, and all the values between those angles, it's negative, and that tells us that it goes like this. right? 3 pi over 4, that's here. We're back out to our 45 degrees, somewhere around 0.7. 5 pi over 6, we're at 1. That tells us it comes out to here again. So you can tell it trends like this, comes back through the pole, and then comes up like this. I missed our point, but you get the idea. It's roughly like this. Hits there, comes back down like that. So these are referred to the rose petal functions because they end up forming these rose petal-like structures. And you can see once we get to pi, we're back to 0. 7 pi over 6, which is here, gives us -1. That's just back here. So look what ends up happening. We just come back here and we repeat the whole thing again. As we run through all these angles, we end up getting these same values again and again and again. That's why I didn't really have the table go all the way through. So let's look at one more over here. R equals cosine 2 theta. Similar process. I went and put a bunch of different points on a table here. You're welcome to verify this for yourself. I also wanted to state where the maximum values of R will occur, meaning where R is 1 or -1 in this case. That's going to end up being at these angles for 2 theta, and therefore these angles for theta. So let's start our graph. Here at an angle of 0, we are already at our maximum R value of 1. At pi over 6, which is roughly there, we move to 1/2. So that's maybe like here-ish. At pi over 4, we're already back to 0. So you can sort of already see the first part of this graph goes like that. At pi over 3, we are at -1/2. That's maybe here-ish. At pi over 2, we're at -1. So you can see how this shape takes place. It goes through here, comes through this point, hits there. Now we continue. This was at pi over 2. Well, at 2 pi over 3, we're at -1/2 again. That's going to be somewhere here-ish. At 3 pi over 4, we're back to 0. So, you guessed it. Look what happens here. Boom. There's our petal. As we move on, 5 pi over 6, we're at 1/2 again. That's going to be around here-ish. At pi, we're at 1. So, boom. And we keep going. At 7 pi over 6, we're at 1/2-ish again. Maybe right there, about. And at 5 pi over 4, we're at 0. So, this goes like that. Boom, right through there. At 4 pi over 3, we're at -1/2. That's up here. So you can see we end up going like this through here, and we're going to end up making this petal. And guess what happens? That comes like this. Boom. And we're almost done. Boom. There's our graph. And guess what happens? It just keeps on repeating itself like this, through here, through here, through here, through here. And it just keeps wrapping again and again as you progress through your angles around the circle and forms what we would call a 4-petal graph here. And let's talk about how you can tell the number of petals you're going to have and roughly where they are. Before we do that, I want to point out one thing that's true about all these petal graphs. The tips of your petals will always be equidistant. So, look at these. We have 3 petals that means each one is going to be 2 pi over 3 away from one another. A full circle is 2 pi. If I divide that into thirds, I get 2 pi over 3. So from here to here is 2 pi over 3. From here to here is 2 pi over 3. From here to here is 2 pi over 3. When we have 4 petals, they're each going to be pi over 2 away, meaning the maximum, the tips of these petals. Pi over 2, pi over 2, pi over 2, pi over 2. So, when you have an equation of this format, r equals cosine n theta, or r equals sine n theta, here's how you can figure out how the graph looks. If n is an odd number, then there's going to be that many petals. So let's look at an example of this. So if I have something like r equals cosine 3 theta, then I know I'm going to have 3 petals. And furthermore, I know with cosine, I'm always going to have a maximum value at 0 because cosine of 0 is 1. So I know there's 3 petals. I know they are evenly spaced, and I know where one of them has a maximum value. That means there's 3 petals, so they're going to be separated by this angle. So I'm going to have 1 at 0, I'm going to have 1 at 2 pi over 3, and I'm going to have 1 at 4 pi over 3. So I already know the graph is going to look something like this, right? Where there's a petal here, there's a petal here, and there's a petal here. Right? 3 petals, they're all evenly spaced. Let's say we had r equals cosine 5 theta. Well, then I would have 5 petals. I'm still going to have one that's right here at 0. But now, instead of being 2 pi over 3 away from each other, they're all going to be 2 pi over 5 away from each other. That's also equivalent to 72 degrees. So we know roughly there's going to be one at 72 degrees. That's like maybe here-ish. And then there's going to be one at 144. That's maybe like here-ish. And then we're going to have another one at 216. So that's going to be maybe right around here. And then we'll have one at basically negative 72. That'll be like here. So we can start forming our petals. There's one here. There's going to be one here. It's probably going to go like that. There's going to be one here. That one will probably come like that. There's going to be one here. And then lastly, there's going to be one here. 5 petals, evenly spaced out, basically 72 degrees away for each of them. This is a rough drawing again. You're probably going to want to be a little more exact when you make this sketch. But I just want to give you the idea of how you can figure out what these are going to look like. Now, let's say we have r equals sine 5 theta. Well, sine's a little bit different. We still know it's an odd number, so there's going to be 5 petals, but we don't have the luxury of just making our first one at 0. Basically, we know our, quote, first one is going to be when 5 theta is 90, or pi over 2. So in this case, that's going to be when theta is pi over 10, which is instead of 90, divide that by 5 and we get 18 degrees, right? So our first one's at pi over 10 or 18 degrees, and then they're all gonna be 72 degrees apart. So we're gonna have one at 18, but then we're gonna have one at 90 in this case. Then we're gonna go another 72, which will take us to this same reference angle on the other side, right? Then we go another 72, so this will be something like here and here. And we make our 5 petals. 1, 2, 3, 4, 5. So there's sine 5 theta. Same idea. Likewise, if I had sine 7 theta, I would go, okay, there's 7 petals. That means they're each going to be 2 pi over 7 away from each other. The first one is going to be at pi over 14, or I'm just going to divide 90 by 7 and figure out where the first one is, and then keep adding increments and make 7 petals. So you get the idea. All right, now let's look at an even number. If n is even, you're going to have twice that many petals. So for example, if I have r equals sine 2 theta, then I know that's going to be 4 petals. Now, 4 petals, evenly spaced, that means they're each going to be pi over 2 away from one another, or 90 degrees. Now, where is that first petal? It's going to be where 2 theta is 90 degrees, or where theta is pi over 4, 45 degrees. So at 45 degrees, we're going to have 1, and then we go 90 away for all the other ones. So this is pretty straightforward. They're all just going to be at the 45 degree angles, right? So we're going to have 1 like that, and then 2, and then 3, and then 4. Sine 2 theta, 4 petals. Let's say we had sine 4 theta. Well, then we're going to have 8 petals. How far apart are they? Pi over 4 away from one another, which is 45 degrees. Where's the first one? Where 4 theta is 90, or pi over 2, meaning theta is pi over 8, aka 22.5 degrees. So they're all 45 away from each other. The first one is basically halfway between 0 and 45. Like, let's say 45 was here. So the first one's going to be halfway between, so maybe there, right? Then we're going to have another one at the halfway point, so like there. And then another one there. And then another one there. And then here. And then here. And then here. And then here. So you just draw your petals. 1, 2, 3, 4. Right? Kind of cool looking. Rough sketch of it. Just to seal the deal, let's say we have cosine 4 theta. We already did 2 theta on the other side. So 4 theta, we know we're going to have 8 petals. The only difference is our first one is at 0. We still know they're going to be 45 away from each other, so we're going to have one at 0, one at 45, one at 90, this 45, here, 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 and here, roughly, right? That's probably, should be in a little bit, never mind that. So this will look like here, and we'll have one here, and we'll have one here, whoops, we'll have one here like that, right? Boom, 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 boom. These are just rough sketches, guys, just to give you an idea. 8 petals, all evenly spaced. And lastly, let's say we have cosine 6 theta. You're gonna go, okay, I have 12 petals. I take 2 pi and divide it by 12. That means they're each pi over 6 or 30 degrees away from one another. The first one, since it's cosine, is always going to be at 0. And then I would just keep moving, 30 and then 60 and then 90 and just start drawing them all. Okay? And there would be 12 all the way around. If there's a number in front, that doesn't really change much. It just changes our R value. Instead of the radius going all the way out to 1, it'll go all the way out to whatever this number is. Like if this was 3 cosine 6 theta, then I would just be saying this is 3 away from the origin instead of just 1. So all that really changes is the distance, but that's all scaled anyways. It's whatever number you put there. All right, so that covers the rose petal graphs. Now let's look at some of the other ones. So other than the petals, the majority of our polar graphs are going to fall into this format here. R equals some number plus or minus something cosine theta or something sine theta. And they'll pretty much all form what's called a limison or a cardioid. You probably don't need to memorize these things, but I'll show you some examples of how we graph these. R equals 1 plus 2 cosine theta is going to produce this table of values. You'll notice that the largest R value that I get is at 0 and again at 2 pi. So that means out here. Now, I put these just so you could sort of see the values it runs through, but really for the rest of the table and what we want to focus on are kind of these whole number results. Like at pi over 3, we're at 2. At pi over 2, we're at 1. Pi over 3, we're at 2. So 2 is maybe somewhere like here-ish or here. So you can tell like we're going to go from here up to there and then through there. That's what we have so far. So we know our graph is something like that. Okay, now pi over 2, 1. At 2 pi over 3, we get to 0. So 2 pi over 3, that's like here. That means we're going to run through this and be there for a little bit. We're going to be in that quadrant for a little bit until we get to 2 pi over 3. Then at pi, we're at -1. So that's here. So that means it's going to look like this. Come through here, dip down, hit right there. At 4 pi over 3, we're back to 0. But that means between pi and 4 pi over 3, we're going from -1 to 0. So that means it's going to just go like this until we get to 4 pi over 3. At 3 pi over 2, we're at 1. So there you go. At 5 pi over 3, we're at 2. Again, that's going to be like here-ish. maybe there, boom. This would be a limosome with an inner loop. And anytime this number is less than this number, you're gonna end up getting that inner loop feature. Now, when these numbers are the same, you'll have what's called a cardioid, which is what we'll look at next. So let's look at r equals 2 plus 2 sine theta. Now, I went ahead and changed it to sine. If it were cosine, like the previous graph, it would kind of be shaped this way. Like it would be pointing towards the positive x-axis because that's where cosine is at its max value. Because this is a sine graph and both these are positive, it's going to be oriented this way. And you'll see that from these values. Now, I'm going to sort of go through this a little faster. I'm going to plot points to help me graph it. 0, 2, pi over 6, 3. So that's going to be maybe around here. And then we'll hit our max value at pi over 2, 4. And then I want the same thing on the other side. So maybe around there. And pi 2. So that'll be about here. And then 7. So then I'll come. See, this is the part where one thing that's important with all these is understanding, like from 7 pi over 6 to 3 pi over 2, I go from 1 to 0, right? So my R values travel from 1 to 0. And then as I move back out to 11 pi over 6, they travel from 0 to 1 again. So I'm going to end up getting like this sort of shape from there to there, and then again from there to there. And then I can sort of see how this whole thing comes about. Something sort of like this. That's why it's called a cardioid. It forms, you can see, kind of an upside down heart shape. Boom, boom. All right. So that's our cardioid, and we'll look at a couple others that'll still be limosomes. Here's a couple more of these formats. So r equals 3 minus 2 cosine theta. When you are looking at these, it's kind of helpful to figure out, well, where is r at its biggest value and where is it at its smallest value? In this case, since we're subtracting a value from 3, we want, when this is 1, r is going to be its smallest, because that's the most we'll be able to subtract from 3. So that basically means when theta is 0, or 2 pi, so here. And when is r its largest? Well, it's when cosine theta is -1, because in that case, we're going to be adding the most we can to 3, because we'll be subtracting -2 or adding 2, and that's going to happen at pi, so over here. Now, I'm going to go ahead and sort of sketch these points out. 0, 1 puts us here. We know at pi over 2, we're going to be up at 3. And at pi over 3, we're at 2. So that's going to sort of end up looking something like this, right? Then as we move, we know we're going to go all the way out to here. But what's going to happen is at 2 pi over 3, we're at 4. So that's maybe there-ish. So we're going to have something like this. And then, like most of these graphs do, we really just end up seeing a symmetrical thing on this side. So that's going to be like that. Sort of like this, out to here. And this gets called a limosome with a dimple. It's got kind of this dimple in it. Let's look at one more. Let's say we have -4 plus 2 sine theta. Now, I can already tell how this is going to be oriented. Let's look back at the previous one for a quick second. Because it was a cosine graph, it's a plus or minus b cosine theta. It's going to either be oriented in the positive or negative x direction. And in this case, because I'm going to get my largest r value when theta is pi, that's here, I know it's oriented this way. So let's look at this one. Here we have a sine graph. So it's either going to be oriented this way or this way. Well, I ask myself, when is r going to be at its greatest value? And that's when this is negative 2, because then I'm going to get an r value of negative 6. Well, because r is negative at that point, which will be at 3 pi over 2, because that's when this is negative 2, it's actually oriented that way because at this angle, r is negative, which means it goes up that way. So whatever this graph does look like, we know it's going to be facing kind of up like that. Now, as I go through and plug in the different values, at 0, I'm at negative 4, okay? At pi over 6, I'm at negative 3. That's kind of like here. And then at pi over 2, I'm at negative 2. That's kind of like here. So we see we end up getting something like this. Probably could be drawn a little bit better, probably like that right there. And then I end up going as high up as 6 on this side, and it essentially just looks like this. That's a convex limicon, meaning it doesn't dimple on this side or it doesn't come in with the inner loop. It just stays kind of in a convex manner. Now let's say I instead had just 4 plus 2 sine theta instead of negative 4. Well, what would change? Let's look at how that would change this graph. All that's going to happen, if you look at these values, instead of these r values at 0, what am I going to have? I'm going to have positive 4. At pi over 6, I'm going to have 5. At pi over 2, I'm going to have 6. And then 5, and then 4, and then 3, and then 2, and then 3, and then 4. So what happens? Well, it actually ends up producing roughly the same graph. I have at pi over 2, I reach a value of 6. At 0, I'm at 4 instead of being at negative 4. So that just means I'm there. Same thing at pi, I'm now at 4 instead of negative 4. Well, that's just there. So then what ends up happening is at 7 pi over 6, instead of being over here, I'm just here. At 3 pi over 2, I'm at 2. So funny enough, we actually end up with the same looking graph. That's probably come out a little more here. That could be there. So what's interesting is we notice, like, if this number is double that number or greater, you end up with a convex limicon. If this number is more than that number but not quite double, you're going to get a limicon with a dimple. If these numbers are equal, you're going to get a cardioid like we saw before. And if this number is less than that number, you'll get a limicon with an inner loop like we saw before. So that covers all those graphs. There's only one type of graph we have left. All right, last we have what's known as the spiral of Archimedes. That's any graph in the format of r equals something theta, like r equals theta or 2 theta or 3 theta. So let's look at it. Graph of r equals theta. Basically what's going to happen when you're at an angle of 0, you're at an r value of 0. And as your angle increases, your r value increases in a linear fashion. But you can picture, since we're in a polar setup, that's going to actually curve it, but it's not going to grow exponentially. So it's going to end up forming something like this. As I get further and further away, right? That's what we end up getting, this sort of shape. And of course, if this was r equals 3 theta, it's still going to look like this. It's just how I choose to scale everything, right? For instance, here in this case, when will I reach an r value of 3? Well, that will be when I'm at an angle of 1 radian. That's somewhere around here. So in this case, I'm scaling it much bigger. We could see a shrunken down version of this graph, and it would look a little bit more like, like this. Right? The spiral of Archimedes. As your angle increases, your distance increases, and it creates this sort of shape. There's a lot of cool polar graphs. If you're up for it, I would check out something different than polar graphs, but what also creates cool images is something called the Mandelbrot set. Perhaps I'll do a video on that someday. I think it's one of the coolest image things you'll see in mathematics. That's different than this section where we're graphing polar functions. That's dealing with the complex plane and an iterative function. But anyways, this should cover everything you'll really need to know how to graph for your classes in the graphing polar equation section. So good luck.